Hello students, welcome to the class of complex analysis. So we start this class by introducing the proposition. Let f be analytic function in the disk BAR. That means we are considering a point in the complex plane A and with a particular radius R. Then you consider an open ball, or it is a disk with the centered at the point A with the radius capital R. Okay. And f is a function which is analytic in this region, in this disk, and gamma is any closed rectifiable curve. Gamma is any closed rectifiable curve. That means its length is finite quantity, rectifiable curve. Then if you integrate f along this curve, then that integral value will become 0. Okay, then this integral value will become 0. So in an open disk along any simple closed rectifiable curve, integral of that function along that curve will be 0. Okay, proof. So let f be analytic. Let f be analytic in the disk BAR. Okay, then we know that any analytic function on a disk will have a power series expansion. Then fz can be written a power series expansion sigma n equal to 0 to infinity an z minus a raised to n for the region mod z minus a less than capital R. Okay, now take capital Fz is equal to, I take a function capital Fz which is equal to sigma n equal to 0 to infinity an divided by n plus 1 z minus a raised to n plus 1. I define a function Fz is equal to another power series expansion. This can be written z minus a into sigma n equal to 0 to infinity an by n plus 1 z minus a. Okay. Now we consider the radius of convergence of Fz, the power series of Fz. Suppose let R dash denote radius of convergence of the power series of Fz is equal to z minus a into sigma an by n plus 1 z minus a raised to n. Then by definition we know that it is equal to 1 by limit supremum of mod an raised to 1 by n, right, which is equal to 1 by limit supremum of, we consider an divided by n plus 1 raised to 1 by n. Actually we are considering the power series of radius of convergence of this series. Okay, this series, and I denote, we consider this term. Okay, consider 1 by limit supremum of mod an by n plus 1 raised to 1 by n. That means the actual coefficient of nth term of power series is an by not an by n plus 1. So we are considering this kind of power series first of all, then you can take the coefficient an by n plus 1 raised to 1 by n. Okay, so which is actually equal to 1 by limit supremum of mod an raised to 1 by n. What happened to limit supremum of mod n plus 1 raised to 1 by n? That is actually equal to 1. You consider n plus 1 raised to 1 by n. Okay, so this can be written e raised to 1 by n log of n plus n, right? So which is, and we know that log of n plus 1 is a term tends to 0. Therefore n plus 1 raised to 1 by n is a term tends to e raised to 0, and that is equal to 1. So its limit supremum is actually equal to 1. Therefore we can omit this term because its maximum value tends to 1. Right, so which implies R dash will be nothing but, and which is equal to limit supremum of 1 by limit supremum of mod an raised to 1 by n, and this is radius of convergence of the given series f set. Okay, so which is equal to r, that is radius of convergence of small f set. So now we get radius of convergence of small f set and radius of convergence of capital F set are equal or same. So which implies capital F dash set is equal to small f set, because you see this is capital F set is equal to sigma n equal to 0 into a n by n plus 1 z minus a raised to n plus 1. And small f set is equal to sigma n equal to 0 infinity a n z minus a raised to n. So only change is capital F dash z is equal to small f set, right? Capital F dash z will be, what is capital F dash z? Capital F dash z is equal to, when you find out n plus 1 into z minus a raised to n, divide, and this n plus 1, that thing will be cancelled, so you get a n z minus a raised to n. So we can see that this is equal to f set. So which implies capital F dash z is equal to small f set. That means the power series of f z is equivalent to power series of f dash z, which will be true only when the radius of convergence are true. Radius of convergence are same. So which implies integral over a gamma f can be written integral over gamma capital F dash z dz, and which is equal to integral and derivative will be cancelled, f beta minus f alpha, where alpha and beta are the range of gamma, where alpha and beta are the limit of gamma. Okay, so you get f beta minus f alpha. And what is f beta minus f alpha? We have gamma is a closed curve, therefore its initial and final points are same, therefore the range of initial and final values will be actually equal, therefore this will be equal to 0, so that integral over gamma f will be equal to 0. Okay, now we will discuss what is a zero of analytic function. So suppose we have an analytic function such that f of a equal to 0. So for example, suppose we consider f z is equal to some z square plus 2z plus 1. Okay, then f is an analytic function, right? Then take a equal to minus 1. So what is f of a? F of a is f of minus 1. F of minus 1 equal to 1 minus 2 plus 1, that is equal to 0, right? So we see that f of minus 1 equal to 0. So that we can say a is a 0. A equal to minus 1 is a 0 of the analytic function f z. And what about its multiplicity? Its multiplicity is defined by when f z can be written z minus a raised to m into another function g z, where g of a non-zero, then this power m is called the multiplicity of the 0 a. Okay, for example, here now f z can be written actually z plus 1 square into 1. So z plus 1 square into 1 is z square plus 2z plus 1, right? So this is nothing but z minus 1 the square gz, where gz is equal to the constant function 1. Okay, so fz can be written z minus a square into gz, where gz is equal to 1. Okay, what about g of a? G of a equal to g of minus 1, and see gz is a constant function, so whatever the value for z, that will be 1 always. So clearly it is non-zero, right? Gz is non-zero. So we represent fz as z minus a raised to m into gz, and note that g of a is non-zero value. Therefore we can say that a equal to minus 1 is a 0 of the function fz, and its multiplicity is equal to 2. And its multiplicity is equal to 2, which implies a equal to minus 1 is a 0 of multiplicity, 0 of fz, which multiplicity 2. Now we will define what is an entire function. You know, entire functions are functions which is defined and analytic in the whole complex plane. Functions which are defined and analytic in C. All the points of C. ഇപ്പോൾ സിയിൽ മുഴുവനായിട്ടും ഡിഫൈൻഡും അനലിറ്റിക്കും ആവുകയാണെങ്കിൽ ദാറ്റ് കൈൻഡ് ഓഫ് ഫങ്ഷൻസ് ആർ കോൾഡ് എൻറ്റയർ ഫങ്ഷൻ. ആൾസോ വി ക്യാൻ കോൾ ഇൻറ്റഗ്രൽ ഫങ്ഷൻ എൻറ്റയർ ഫങ്ഷൻ ഓർ ഇൻറ്റഗ്രൽ ഫങ്ഷൻ. Entire function or integral function. The examples are all polynomials are entire function. All polynomials, complex polynomials are entire function, entire or integral function, and exponential function is an entire function, right? So that we can say when a function is entire, if fz is entire, if fz is an entire function, then which is clearly analytic, then it is analytic, right? Then it is analytic. So when a function is analytic, it has a power series expansion. Therefore every entire function will have a power series expansion of the form sigma n equal to 0 to infinity a n z minus a raised to n in some region for mod z minus a less than some r. And note that here when the function is entire, then radius of convergence will be equal to infinity. When the function is entire function, then the radius of convergence will be equal to infinity. Now we move to the very famous theorem in the complex analysis, very important theorem in the complex analysis, Leovely's theorem. If a function is bounded entire, then it is a constant. Every bounded entire function is constant. So that I can say boundedness plus entireness. Entireness will together implies function is a constant. Analyticity plus boundedness in the whole complex plane will be leads that function into constant. Okay, how will you prove this theorem? It's a very important Leovely's theorem. So suppose f is a bounded entire function. Suppose f is an bounded entire function. So since it is bounded, which implies there exists a number, real number m such that m greater than 0 such that modulus of fz will be less than or equal to m for every z in the complex plane. Okay, ready. So when the function is a constant function and when the function is bounded, we will get mod fz is less than or equal to m. Okay, since f is entire, since f is an entire function, then f is analytic everywhere. So when you have an analytic function, we can use the Cauchy's estimate. Therefore by Cauchy's estimate proposition result, modulus of fnth derivative of a will be less than or equal to n factorial into m divided by r raised to n. Right? R raised to n. Okay. Therefore, what you get now? Which implies, now take n equal to 1. Therefore, modulus of f dash of a will be less than or equal to 1 factorial m by r. That is m by r. Okay. Taking the limit as r tends to infinity. When r is tends to infinity, then what will happen to modulus of f dash of a? This tends to 0 for every a. So which implies derivative of that function is actually equal to 0 for every point z in C. So which implies derivative is equal to 0 means that function is a constant function. F is a constant function. So very easy to prove only by using the boundedness concept and Cauchy's estimate theorem. As a consequence, we can prove one more result that you can take as a corollary. It says that if f is non-constant entire function, if f is a non-constant entire function, that means if there exists an entire function which is non-constant one, that means we are not taking a bounded function. Okay, then limit z tends to infinity fz will be infinity. Then limit z tends to infinity fz is tends to infinity. Suppose there is an entire function which is a non-constant function, then limit z tends to infinity, fz is infinity. So remember, when a function is entire and bounded, then it will be constant. If there is a function which is entire and non-constant, then its limiting value will be equals to infinity. Because it can't be bounded, right? How will you prove this result? So let f be a non-constant entire function. Okay. And assume that, suppose that limit z tends to infinity, fz is equal to some particular number a. Then what will happen? So which then there exists some r greater than 0 such that we can find out some fz such that fz minus a is less than or equal to some 1. If mod z is greater than some r. Right? That means we are choosing the value for epsilon equal to 1. Taking epsilon equal to 1. Right? Okay. Which is greater than r. Which is that is limit z tends to infinity fz is equal to a means when z tends to infinity, that means when z is larger, that is mod z is greater than or equal to some particular r, when r is greater than a large number, then the distance between fz and a is very very less, so that we can consider the distance between them is less than or equal to some epsilon. That epsilon is taken as 1. Okay. Now consider fz minus a, fz minus actually f of z minus a, the term f of z minus a inside the disk mod z less than or equal to r. So now considering the value of fz minus a inside the disk fz less than or equal to r. Okay. Since our function is entire, since f is entire function, it is analytic, right? It is analytic. Okay. Analytic in, what about this set? Mod set less than or equal to r. Mod set less than or equal to r is a compact set, right? It is a compact set. Therefore, since fz is analytic, fz minus a is also an analytic function, right? Therefore, fz minus a is it is analytic in the compact set. Mod set less than or equal to r. Therefore, fz minus a is also analytic in the compact set. Mod set less than or equal to r. Okay. Right. So analytic functions are continuous. Therefore, fz minus a is continuous on mod set less than or equal to r. You know that every continuous function on a compact set is bounded. So which implies fz minus a is bounded. On mod set less than or equal to r. So which means modulus of fz minus a will be less than or equal to some m, where m is greater than 0. And for every set in mod set less than or equal to r. Okay. Just applied the definition of boundedness. Okay. So which implies mod fz minus mod a, that will be less than or equal to modulus of fz minus a, that is less than or equal to capital M. So which implies modulus of fz is less than or equal to m plus mod a. Okay. So which implies f is a bounded function. Right? F is a bounded function on mod set less than or equal to r. Mod set less than or equal to r. And this r may be any positive real number. When r tends to infinity, which implies f is bounded on complex plane C. And what is f? An entire function. So which implies f is bounded and entire function on C. So by Leovely's theorem, every bounded entire function is a constant function, right? Therefore, by Leovely's theorem, f is constant. Is it possible? No, it is not possible. By our assumption, fz is a non-constant function. So, which is a contradiction? Which is a contradiction. Contradiction. Therefore, what happened? There exists no r such that this thing is less than any particular number. Therefore, this will always goes to infinity. There is no number a with the required property. So, which implies limit z tends to infinity, fz is always goes to infinity. Okay.